All right, next up we've got Patrick Margavio and Scott Hayden. I apologize if I butchered that. Talking about additive oscillating heat pipe development for electric aircraft thermal management system and waste heat recovery.
My name is Patrick Margavio, and I work with Thermoblant Technologies. I work with Alex, actually. He was our previous presenter. And my colleague, Scott Hayden, is also on the call here. Scott, do you want to introduce yourself?
Hello, I'm Scott Hayden. I'm a thermal engineer here at Thermoblant Technologies.
Yeah, so this is a presentation on some SIBR work that we have been working with NASA on over the last approximately 9 months or so. We had a phase 1 SIBR and then a follow-on phase 3 that most of the reporting for this comes from that phase 3 through NASA Glenn with Roger Dyson's team. The need is for thermal control of a solid state circuit breaker that the Naval Postgraduate School designed for Roger's system. The heat generation from that is basically 5 kilowatts of waste heat from a 1 megawatt electrical system at 99.5% efficiency. NASA uses thermoacoustics in order to do waste heat recovery throughout the aircraft. So they're transporting thermal energy over long distances using thermoacoustic tubes. We're basically serving as the interface between that circuit breaker component, which is generating that waste heat, and the system transporting that energy throughout the aircraft. So I think of it as a square peg and round hole kind of problem. There's a square surface of the Infineon device, and the thermoacoustic tube is a round rejection boundary from the oscillating heat pipe. There's some key performance characteristics that I kind of captured here to show what we expect to see from the oscillating heat pipe advantages that it represents. So there's design flexibility on the power electronics. We're able to change the orientation quite a bit in a variety of different cases. I didn't show in the presentation what all those different cases were just for lack of time, but we can move the components within the device into quite a few different orientations, providing design flexibility to the NPS team. We have a dramatically reduced cycle time. In our phase 1, we had 3 builds, and normally in a phase 1, we can only get 1 build within the time frame. The additive process allows us to explore form factors that are either impossible or very challenging in conventional fabrication methods for oscillating heat pipes. The key power requirements here were 5 kilowatts of performance with 4 kilowatts per kilogram. And we were able to go beyond the 4 kilowatts per kilogram target, as I'll show later on in the presentation. The NASA team also wanted us to demonstrate gravity independence of the performance, which we were able to demonstrate, and to demonstrate that our predictions lined up with performance. So Alex talked a lot more about that thermal for his project, and we have a little less thermal information in this presentation, but we were also able to demonstrate that. When we were doing the discussion with the NASA team about the specific the application specifics, we discovered a couple of very interesting ways that the OHP can enhance the performance. So most of the time, the OHP can't influence the thermal load. But what's very interesting about this is the efficiency of that device is actually driven by the temperature limit of the device. So the 99.5% efficiency is assuming the device is below 150 C. But if we can make sure that we're below 120 or even most likely below 70 C, we can dramatically increase that efficiency and therefore reduce the actual thermal load that we're seeing. So depending on what that efficiency ends up being, if it's 99.6%, for example, it would be 4 kilowatts of power instead of 5. So we're actually able to reduce the thermal load, which is rare in OHP applications. The other thing that we realized in exploring the application is that the specific voltage level decided by the NPS team is limited by temperature as well. That they had to select a 3.3 kilovolt system, but a 4.5 kilovolt system would be enabled by keeping the circuit breaker below 60 degrees C. So by by enabling that kind of temperature control, we're able to go to a 4.5 kilovolt system instead of a 3.3 kilovolt, which is a performance increase of about 37%, or could be represented as a reduction in the number of devices needed throughout the aircraft, and therefore weight reduction. We actually presented on the first phase of work in spacecraft thermal control workshop. So I kind of summarized that in just this one slide, where we did some thermal modeling and physical construction of this, the OHP shown in the center of the slide. And that OHP, you can see the square peg round hole kind of metaphor there, and the reduction in temperature by below approximately 65 degrees C. And then the objective of the phase 3 effort was to take this work, which was not quite the right geometry and had a few compromises in terms of aspects of the design in order to get it fabricated within the phase 1 to account for those things, and then scale up to a full scale system, being able to go from the 1.7 kilowatt system we tested in the phase 1 to a 5 kilowatt system while maintaining the 4 kilowatt per kilogram or better specification. So a lot of that started out with some material evaluation. I don't know, Scott, if you wanted to add anything on the thermal modeling side of the phase 1.
Sure. So from the thermal modeling side of the phase 1, basically the comparisons that we made were between a solid aluminum conductor that would couple the Infineon device to the thermoacoustic heat pump, and then comparing that directly to our OHP and observing, or basically from simulation, seeing what is the decrease in temperature by switching to an OHP, and then what is the increase in specific power by switching to the OHP.
Cool. So we did a bunch of material evaluation. We don't have time to dig into all of it, but we looked at feature size evaluations where we looked at a variety of different features to see how well controlled we could print those small features in the 10 thou range and even down to the 7 thou range. We also looked at a variety of material properties, CTE, thermal K, and a couple of things that we'll dig into a bit more on the next couple of slides, including some burst testing results.
So for understanding the material properties, the material that was used for printing these aluminum OHPs is the ALSI 10mg aluminum alloy. The majority of OHPs that are formed by OHP, the Thermovant, are made in aluminum 6061 or aluminum 3003. So for the printing of this new alloy, we wanted to make sure that we understood the tensile strength of the material. So in the first phase of the project, we basically printed coupons that for aluminum 6061 we knew we would be able to fail with our hydrostatic pressure test station that we have here at Thermovant. So we printed those in this new material, and then we attached those to our hydrostatic pressure test station and basically observed, whether it failed above or below where we expected 6061 to fail, or T4 6061 to fail. If you want to jump to the next slide, Patrick. So from those burst pressure coupons for 6061, so we know that printing parts typically print proud of, say, their input design file. So we did have to adjust our simulation for knowing that the parts are printed proud. So maybe hole diameters are smaller, or the skin that we are bursting is actually thicker than we expected. So for 6061, we expected these pressure discs to rupture at 1900 psi, but we found for the ALSI 10mg alloy as printed, the minimum rupture pressure was 3500 psi. So that was a good indication from one data sheets and this first first coupon test that the ALSI 10MG, at least as printed, is stronger than aluminum 6061 T4. To further understand that, we also printed tensile test bars and tested those in a tensile tester and found that data also matched well to ALSI 10MG data sheets, which suggests that as printed, ALSI 10MG is about 1.7 times stronger tensile strength than aluminum 6061 T4, and then also is stronger than 6061 when it's heat treated to a T6 heat treatment.
Yeah, so this is kind of a pretty exciting result that the as printed material, we definitely expected it to be worse than our standard aluminum 6061 bulk material. And the fact that it's better is a really nice surprise that might open up some interesting opportunities. So then we also went into other material testing, just trying to understand, CTE and a variety of other things. The one I think that's somewhat interesting here is the thermal K. So we saw a pretty decent variation in the thermal K with print orientation. So the measurement of the thermal K with respect to the angle that the parts were printed at drove a at least 20% variation in the thermal conductivity. So that suggests that when designing OHPs with this printed alloy, that we need to take into account the print orientation with respect to especially the heat input, or if the heat rejection is the highest heat flux, that the heat rejection boundary might need to be designed in a specific orientation with respect to printing. So that's kind of the sort of high-level summary of the material evaluation campaign that we went through for this. So then I put a couple of slides together on when we did scale it up, what did we see in terms of results. So we had a couple of different ideas on how to integrate. We tried welding technique and what's shown here as soldering technique. We also found a shop shortly after this, the end of this phase 3, that enables printing on a scale where we could actually just print as one full system. So we have another project that's following on from this where we think we'll probably just print as a full system with being able to avoid some of the integration efforts, because there's extra steps required, for soldering onto of the aluminum into an integrated stack. We needed to perform nickel plating, for example. So things that we could maybe save some production steps by being able to actually just leverage a larger printer system is one of the things that we're probably going to try in this follow-on project. We were able to demonstrate higher than the 4 kilowatt per kilogram target in thermal testing. The predicted value that we thought we could hit was 5.7 kilowatts per kilogram, and we were able to demonstrate 5.61 kilowatts per kilogram. We actually weren't still in this test. We weren't actually limited by the OHP performance. It was actually a test bed limitation that prevented us from going above 5.7. So there's a chance that we could go a little higher in the power per kilogram than the demonstrated 5.61. And we did run into an issue in actually testing the full scale 5 kilowatt system. We created a test bed capable of testing actually quite a lot higher than the 5 kilowatts with some headroom, and demonstrated that test bed was capable. But for some reason, this particular print run, the overall OHP system demonstrated some unstable performance that we weren't quite able to determine the cause of within the construct, within the time frame of the phase 3 effort. So we do have a follow-on project, and we're going to continue to explore what caused the issue we saw with this full system, but didn't have time under that contract to run that issue to ground. So kind of running through some concluding remarks here. Definitely, we were able to demonstrate a dramatic increase in the prototyping speed with additive approach, around 3 weeks of fabrication time instead of around 3 months. And we were able to demonstrate this particular design. We actually could fabricate in a very complicated and expensive braid stack if we wanted to, but we actually, basically the additive technique allowed for cost competitiveness of this particular approach. We were able to demonstrate a low thermal resistance heat sink for the fault management system. We have an active phase 2 SIBR, which is associated with this work that is leveraging what we've been learning here into higher temperature materials, including Inconel 625 and 316 stainless steel. And we are looking at adding to the waste heat recovery application on another part of the aircraft, specifically trying to draw heat from the turbofan for waste heat recovery in that part of the system as well. And then the last bullet point there is just we're exploring quite a few different applications within the electric aircraft here. This one is electronics. In the phase 2, we're looking at turbofan, and we've already demonstrated battery thermal management and thermal skin heat rejection in some other NASA-funded SIBR efforts. So we're pretty well positioned to attack a variety of problems within the electric aircraft thermal management system. I see a question in the chat about the working fluids that we explored. So this is the envelope is aluminum, silicon 10, magnesium, and the working fluid is ammonia. So it's similar in terms of operation to some of the ammonia aluminum OHPs that we manufacture on a regular basis. So there's another question is, does the working fluid transmit through additively manufactured wall? So the only thing we saw strange in terms of the additive structures on the inside walls of the OHP is that the ammonia can get trapped in small features in the roughness of that surface and take longer to evacuate for subsequent processing. But it doesn't pass through the wall, but the texture does trap the ammonia to make it take slightly longer to charge.
There's a question, the channels are 3D in the printed part?
Yeah, that's right. I can scroll up to one of the images here. Yeah, if you see the parts, the channels are in the plane that's flat against the tray here. The channels are in the surface that is against this tray, the backside here. And then they travel up into a second dimension here. You can see this edge that steps up. That's the channels moving up into a second plane to travel, to change orientation. And then they're actually traveling within that region into the base of this arc, and then up into the arc, and then out and back. So we're trying to make sure there's good communication between the fluid and the heat input, as well as the fluid and the heat rejection. So there's a pretty complex internal channel routing present in this one.
Okay, looks like there's another question. Is particle shedding a concern in the 3D printed part?
We don't see particle shedding from the parts, but we do see remnant powder left behind from the initial print that needs to be flushed out. We actually have a provisional patent filed on the methodology that we're using to flush the powder out.